Hello, my name is Johnatan Ivanov. I am 21 years old and a senior at the University of Pittsburgh, applying to vet school this summer. Where's me? Whoops, there you go. And today I will be going through how to find the center of mass for Region 1 in Project 2. Just to show the date and time, so current date, August 15th. And then down here on my calendar, you can see 2024, August 15th. And then here is the presentation that I'll be running right now. So I'm going to be going through step 17 of Project 2, which was finding Region 1's center of mass. So I did this using polar coordinates, which are just like a it's like a point being used as an angle of rotation, and then like calculating or extrapolating like from that. So this involved a little bit of like trig and some integrals. So, well, excuse me. To start with, we have to kind of define the center of mass, and so we're going to be using these coordinates here. X and y. X is on the x coordinate, or the x value is on the axis of symmetry, so that's just 0 because it's right on the y-axis. So we're looking for the y value. And so here, y dm is the moment at the x-axis, and then dm down here is the total mass. So in polar coordinates, y, or the y coordinate rather, can be represented with r sine theta over here. And then to talk about the area, we'll be using this expression right here, r dr d theta, and then dm from up here, that's the mass that can be represented with this rho r dr d theta. So this rho right here representing density. So now going through the integrals, r1 is bounded by these two integrals here, with theta being in between 0 and pi, greater than or equal to, and then r being less than or equal to, or less than or equal to 35, greater than or equal to 25. So onto the numerator, which I said was ydm. Here we can kind of apply our integrals, and then subbing out our definition for dm right here. And then down here we do the same thing with y. We substitute that r sine theta in for y, and then we have this this nice pretty looking numerator up here, totally not a mess at all. And then down here, the denominator, much more simple, just the one value for dm, also bound by the integrals. So now we can evaluate these. And up here, so we have our two parts of the numerator. We have the rho sine theta d theta, and then the r value. So we evaluate these integrals. We'll take it step by step. So this first part right here, you take the derivative of sine, you get negative cosine. You evaluate the integral, and then you'll get 2 rho. Here a little, or just as easy, just with some numbers now. We will take we'll evaluate the integral with respect to r, and then we'll get this value down here, which, yeah, it's just evaluating the integral, and that will make up our numeral, these two values. Onto the denominator, which also just a little bit simpler. Same thing. So we have our rho value here, on the integral of 0 to pi, and then r is still bound by 25 and 35. So with respect to our rho d theta, that can just be converted to rho times pi, and then same thing down here, except instead of it being r squared, it's just r, so then we'll take the antiderivative, we'll get r squared over 2, and then we'll evaluate the integral via that. We'll get 300 pi rho. Oh, I think I called that r earlier. My apologies. That should be rho. For the expression in full as 2 times rho times 9,083.33 all over 300 pi rho. So now we just go about solving that nice and easy. The rows cancel out, so then we're just left with this number. You just plug that in the calculator and you will get 19.275, which you can round to 19.3 for our y coordinate, and then our x coordinate is 0, so that will put us along the axis of symmetry into region 1, up 19.3 feet according to that graphic. And then that's how you calculate the center of mass for that region 1 with those two bound semicircles.